In this video, we will move on to begin the discussion of calculus related to polar curves. So the first thing to think about, similar to parametric equations, would be if we have a polar curve, can we still find dy dx? That is what we would think of as representing the slope of a tangent line at a given point. And the answer is yes, we can in a very similar fashion as to parametric equations. So what we need as a starting point is that we have x equals r cosine theta and y equals r sine theta. And a very important observation to make is that it appears at first that x and y are depending upon two variables, both r and theta. But note that r is only a function of theta, so r and cosine theta both only depend upon theta. So what we can do is rewrite dy dx as being dy d theta over dx d theta. And the only difference with polar versus parametric is that when we find these two derivatives, dy d theta, dx d theta, they will both require an application of the product rule. Because remember, r is a function of theta. So we're thinking of this as one function of theta multiplied by a second. So for dy d theta, the product rule tells us dr d theta, the derivative of the first, times sine theta, the second, plus the first times the derivative of the second. And the derivative of sine is cosine. Similarly, dx d theta, we would apply the product rule to r cosine. So we get the derivative of the first times the second plus the first r times the derivative of cosine. And the derivative of cosine is minus sine. So I'll go ahead and pull that minus out. And this gives us a representation of dy dx. And just note that there's really only two things that we need to do once we have this formula. We need to fill in two spots, the dr d theta, and fill in two other spots what that function r is as a function of theta. Then if you want to know dy dx corresponding to some theta value, you would just go ahead and plug theta in. So let's look at a few examples. Let's find the slope of the tangent line to the polar curve r equals 2 sine theta at theta equals pi. So let me go ahead and just write down the formula that we want to use. So we have the following formula that we need to work with. So dy dx is really dy d theta over dx d theta. And we've used the product rule in the previous slide to come up with what's in the numerator and the denominator. So we can substitute in directly that each of the two r's that we see will become 2 sine theta. And for the two dr d thetas, we're going to have to calculate dr d theta to plug in. So in this case, very easily, dr d theta is 2 cosine theta. So dy dx, if we substitute in, dr d theta is 2 cosine theta. And then in the top, the sine theta remains plus r cosine. So plus 2 sine theta cosine theta. In the bottom, the cosine theta remains. And we subtract away r sine theta. So we subtract away 2 sine theta sine theta. And what we want to know is not necessarily what dy dx is, which we need along the way. We want to know what this is when we plug in theta equals pi. So for each of the thetas that we see, 4 in the top, 4 in the bottom, we need to plug in pi. And recall, cosine of theta, or cosine of pi is -1, and sine of pi is 0. So any term involving a sine of theta when you plug in pi will be 0. So 0, 0, 0. So 0 plus 0 over something minus 0. And cosine of pi is -1. So 2 times minus 1 times minus 1 makes that first term in the bottom a minus 2. And the only thing that matters in this case is that it's non-zero, because 0 over minus 2 is equal to 0. So kind of a two-step process here. Find dr d theta and use that to get the formula for dy dx. Once you have the desired formula, plug in the value of theta which is given. So one more example involving finding dy dx. And I've written out for us the template just to make our work a bit more efficient. So the curve we're given is r equals sine 3 theta. So for both of the r's in the formula for dy dx, we need to substitute in sine of 3 theta. So sine 3 theta and sine of 3 theta. And then in those remaining first slots in the top and the bottom, we need dr d theta. So by the chain rule, dr d theta will be cosine 3 theta times 3. So 3 cosine of 3 theta. So we substitute those in. So note for these problems, I won't say the most difficult part, but the first difficulty is really remembering the formula. And note, if you remember where it comes from, that will certainly allow you to come up with or develop the formula each time that you need it. And recall what the top and the bottom are. The top would be dy d theta, where you're differentiating that formula y equals r sine theta. And the bottom is dx d theta, where you're differentiating that formula x equals r cosine theta. So we have dy dx, but what we really need is the value of dy dx, that is the slope of the tangent line, when theta is equal to pi over 6. So for convenience here, let's just kind of note 3 times pi over 6 is pi over 2. So, and now just plugging in, working across the top, we have 3 times cosine of pi over 2, which is 0, times sine of pi over 6, which is 1/2, plus sine of pi over 2, because it's 3 pi over 6, which is 1, times cosine pi over 6, which is root 3 over 2. So as mentioned many times previously, it's important to know your trig values. Then in the bottom we have 3 times cosine pi over 2, which is 0, multiplied by cosine pi over 6, which is root 3 over 2, minus sine of pi over 2, which is 1, multiplied by sine of pi over 6, which is 1/2. So note the first term in the top and the bottom is 0. And what we really are left with is positive root 3 over 2 divided by 1/2. So dividing by 1/2 is multiplying by 2, so the 2's cancel, and all we are left with in this case is minus the square root of 3.